Okay, it's now recording.
Yeah, thank you. Okay, just hello everybody. Thank you for joining this webinar. A quick introduction of the European project that basically allowed us to organize those webinars. This is the first of hopefully a series of webinars about modeling applied to membrane technology, and in a measure we are organizing this as Modelta. Michele Ongis, CTO and co-founder of Modelta. So I will also chair this meeting, but I will just give the introduction and collect the questions you might have. But then I will leave the floor to Vladimir for the presentation. So just a few information about the Measure project. So the Measure is actually a 4-year project that is starting soon the last year. The idea is to develop innovative membrane materials for 3 different processes. I will not go into the detail, but basically it's to find more sustainable materials for free membrane application and scale it up to industrial demonstration at TRL 7. There's basically very good consortium, huge consortium of partners all across Western Europe, at least. So we have many partners from Italy, France, and the Netherlands, and also partners from Sweden, Germany, Spain, and Slovenia. Just a few presentation of the partners involved in this activity. So, TNO is that Vladimir is part of. So presents today is a research center in the Netherlands, and the Measure project is also dealing with the modeling activity and with the membrane preparation for the pervaporation process. But they have also expertise in a lot of stuff. It's a big research center, but also in modeling. PNO, Manuel is part of PNO. They are responsible for dissemination and communication in Measure. Generally, it's a consultancy company, quite international, although I think here we are represented by the Italian division. And they make a lot of stuff as like public funding project, innovation, digitalization, market analysis, and so on. While Modelta, which I'm part of, is a startup. We do exactly this kind of thing. So modeling of membrane and digital solution for membrane technology applied to the processes. And in Measure, we are work package leader for modeling, and we're also organizing those webinars. Final remark before to start. So first of all, as I said, this analysis, cycle assessment, or this kind of activities which are commonly required in the modeling activity, but in principle there are several other modeling options. So let us know what are your preference, so we can work on it. And of course, stay tuned by following the Modelta page on LinkedIn and also the Measure project page. We will both mention and we will both give you information about the webinar and make posts about asking your input. What would you like to see next in the next webinar? So this is all I had. Then we leave the floor to Vladimir. He has basically a very interesting presentation, a lot to present. So I will say, let's avoid to interrupt him with questions. You can write your questions in the chat, and if we have time in the end and there are not too many questions, I can select the most relevant, in my opinion, and we can and I can ask the question at the end to Vladimir, or we can find another way to address your questions another moment. So that's all from my side. Thank you very much for your attention, and Vladimir, the floor is yours.
I will share my screen. Yeah, so do you see my screen?
Yes, yep. But not yet in a full presentation mode.
Right, so, okay. So first of all, thanks everyone for joining. My name is Vladimir. I'm a chemical engineer at TNO. For the past 10 years, and not only in TNO, I've been focusing on modeling work with an interest in reactor design and modeling, separation technologies, and advanced process control, but especially at TNO with separation enhanced reactor technology. So like absorption enhanced reactors or membrane enhanced reactors. So today, we're going to look into the membrane modeling in Aspen Custom Modeler, or ACM. So I've been working with ACM primarily for the last few years, but before that I also worked with GPROM's Model Builder and other modeling tools. But today we're going to look into ACM. So today our specific topic is building and optimizing steady-state countercurrent block flow membrane model in ACM, and we're going to look into how to set it up in ACM, how to configure Aspen properties, but also use Aspen property procedures, how to apply domains and use a built-in discretization for spatial modeling, also defining and working with submodels using variable specification, and also formulating and solving an optimization problem in ACM. Just quickly, so what is ACM? For anybody that's not used it before, it's an easy-to-use tool for creating, editing, and reusing models of process units. So you build your own simulation applications and you combine them in a graphical flow sheet. You can perform dynamic steady-state simulations. You can use parameter estimation, optimization, and all in an equation-based manner. So Aspen Custom Modeler provides a systemic way to model and also solve distributed parameter system in which process variables vary both in space but also in time. And these systems are very common in engineering and science, and they're described mathematically by partial differential equations. So why there is a big benefit to ACM is that it includes a wide range of numerical solvers, so different discretization methods, nonlinear solvers, and optimization algorithms. What's also a big benefit to ACM is that it includes Aspen properties. So anybody who's worked with Aspen Plus is familiar with this, and they can be also directly used in ACM, which going to look into the 1D counter current block flow membrane model. So in terms of the assumptions, it's a 1D model. In terms of the components, we're going to look into the CO, CO2, hydrogen, and water. We're assuming hydrogen selective membrane. We're also assuming isothermal conditions, and we're not going to consider pressure drop. Maybe I can just use the pointer. It's going to be easier. So this is going to be our species balance, and this is going to be our permeance term, which is expressed with Arrhenius expression. So our system geometry. So we're going to have 4 ports. We're going to use a feed port, the retentate output port, the input sweep port on the permeate side, and the output permeate port. With our boundary conditions, we need to specify, first of all, 2 different domains. So one on the retentate side and one on the permeate side, where on the retentate side, we're going to specify our boundary conditions at 0, and our permeate side, we're going to specify our boundary condition at the end node. For this sort of a problem, we need to use 2 different domains with 2 different discretization methods, but I'm going to talk a bit more about it later. So this is very basic membrane problem, but you can actually do a lot more in ACM. So I'll just show you quickly also what I've been working with for the past few years. So in terms of 1D model, you can also look into the how to describe a full system geometry, the temperature and pressure effects. You can look into different dynamic, you can look into the dynamic operation, create a custom model flow sheet. You can also look into the process control. So for example, in the Measure project, we're looking into the esterification reactor with the combination with the Pervaporation units. So, but what you can also do is you can deep dive into a single process unit. So this is on the right-hand side, you can see the example of the 2D membrane reactor model that I've developed in the last year. So you can actually look at not only axial, but also important radial phenomena that's very important for membranes or membrane reactors, like radial concentration, polarization, drift velocity, and a lot more. But before we continue to ACM, let's just quickly go through some important model elements. So first of all, variables. So they define the values that can be either fixed or free in the model. So free variables are calculated, fixed variables are fixed. You can use predefined variable types. So for example, like mole fractions, then you get already predefined variable boundaries, so from 0 to 1. But you can also use custom variable types, or for quick use, you can use real variable type, which already has a broad range. For parameters, they define the values that are fixed for the whole simulations, also considering dynamic simulations. Ports, they define the variables that can be passed in or out of the model using streams connected to the model. So for example, if your port carries flow, composition, temperature, pressure, that you can take in the model or take out of the model. You can write your custom ports, but I would recommend to use mole fraction port SI, because that way you can easily export your models to Aspen Plus and they will recognize those ports. Streams, basically streams connect to ports, and they can, for example, connect between an output port in one model and input port in another, and they carry variables. So you can use connection streams for quick connections, but you can also use control signal streams. So for example, they can be used for input and output variables connecting to PIDs, but also other units. And then the last slide, in terms of the domains, well, domains are used to define the space over which an OD or PD system and its corresponding variables are distributed. So you always have to select a discretization method per domain. And in this case, where we look into the countercurrent flow, we need to define two domains with two corresponding discretization methods. And I will also go into a bit more detail on this. So you can also potentially use a single domain for the countercurrent flow. Well, if you want to be mathematically accurate, you would want to use, for example, a central finite difference method or a similar method with boundary conditions on the both sides. But there is also one way in ACM to do it, which is not numerically consistent, but it's accurate. And if we get enough time, maybe I'll show you this also, because it's a, and it shouldn't work, but it works. And then there's component lists and Aspen properties. So you select your components and you define your equations of state similarly to Aspen Plus. So maybe we can start with this because it takes a bit of time to open always. So let me open ACM. Let's carry it here. So where we select our components and equations of state, we go to component list, configure properties. We go to use Aspen property system, and you can import your property file, but in this case, we're starting from scratch. So we go to edit using Aspen properties. And while that is opening, let's go back here. So with the property procedures, this is a very useful tool in ACM because basically you can calculate all the physical properties by just providing temperature, pressure, and composition. So you don't have to add any additional equations, for example, to estimate your heat capacity or activity coefficients. What you can do is just you can call the Aspen property procedures and you provide it with required parameters like temperature, pressure, and you will get the value back, as I said, for example, for density or heat capacity or whatever physical property is available. Okay, now that it's open. So anybody who's worked with Aspen Plus is very familiar with this. This is where we need to define our components and methods that we're going to use. So let's add CO, CO2, hydrogen, and water. And then we click next. And then we need to choose our method because we're going to work at a bit higher pressure. Let's use SRK. And when we're using SRK, we also need to use steam MBS for the free water method. And then we go next. And let's run. All right, and then we close and save properties. Basically, our properties, Aspen properties, are saved now, so we can add the components now. So then we go to the default, and we carry all the available components to the right. You can also select each component which you want, but now we will want all four, and then we click OK. So basically now we can start with model building. We go to custom modeling, go to models, and then we click add model, and let's call it membrane. This is going to be our main code. And you can see here in the comments, so this is how you write a comment in ACM with 2 slashes. You're not actually limited in how you want to define your parameters and variables. So you can do it in any way you like. The only thing you're limited is with domains and distributed variables. You need to define your domain first, and then you write your distribution variables. But I'm going to do it in the way that I'm used to, the way I like it. So I usually define ports first. So let's define ports. I would also advise, if you're just starting with Aspen Custom Modelers, to use Model Assistant. So in the Model Assistant, you have all your variables and parameters and submodels or ports so this way you can define it more easily. So if we go to ports, then let's define our feed port system again. We have 4 ports. We have an input feed, output retentate on the retentate side, and on the permeate side, we have our sweep input port and the permeate output port. So let's define our feed port. It's feed, and then, as I said before, I advise to use mole fraction port SI just because of easy exporting, and then we define it as an input port, and we click insert, and then we have an define feed input port. I will show you actually what mole fraction port SI carries because that's important. So this is a predefined port. You can also build your own port. So if we go to libraries and modeler and port types, here you can find already Aspen's predefined ports. So this is the mole fraction port SI. And what you can take in and take out with this port is the flow rate, temperature, pressure, mole fractions, also molar enthalpy and molar volume. It's also important to note the units. So these are the units that are going to be carried over to Aspen Plus if you're exporting your model. You can use whatever units you want, but if you export it to Aspen Plus, it's going to think it's these units. So just be careful about that. Okay, so let's return to the model. So because we don't have much time, I won't be writing all the ports and the variables myself. So I'm just gonna copy them in the model. So let's copy other remaining ports. So as I said, we have 4 ports, 2 input ports and 2 output ports. Also importantly, ACM is not case sensitive, so this doesn't matter. So we now want to define our domain. As I mentioned before, we have 2 domains. So we have one on the retentate side, I call it axis R, and we have one on the permeate side. So if you look here, our boundary conditions for the retentate side is defined as 0. So that's why we need to use backwards finite difference method, because we have a known value at x minus 1. And for the permeate side, we want to use forward finite difference method because we have a known value at x plus 1. This is what we choose here also. We can use the BFD1 because we have only first order ordinary differential equations. Then we need to define our length. I always define it as 1. You can, for example, define it as a membrane length, but I think it's much more convenient to always define it as 1, and then you can multiply your differential equations or your derivative with 1 over the length value. That way you make a dimensionless model because it's much more convenient for working. Then you also need to define your spacing preference. And basically what your spacing preference does is that your length over spacing preference will define the number of nodes. So this is 1 over 0.025. So this is going to be 40 nodes that we're going to work with, both for the axis R and axis P. Then let's define our distributed variables. So distribution variables are the only variables that are defined differently in ACM. So these are the variables that are present inside your derivative. So in our case, this is going to be component flow rates. So these variables have to be defined in a specific way. So these variables, so because it's a component flow rate, it's in a component list, and it's defined as a distribution 1D. You have to define what is your X domain. So for our retentate component flow rate, it's going to be axis R, and for our permeate component flow rate, it's going to be axis P. You say that your highest order derivative in our case is 1, and you define it of flow mole. So this is the variable type that's already predefined, and we can write a description. So you don't have to write a description, but I like to add a description because I also want to take note of which unit I'm going to use. Then we need to define our other variables. So other variables are defined slightly differently. So they're not defined as a distribution, but still they're calculated from 0 to end node. For example, for our mole fractions, you define it because it's calculated for every component, and we're going to calculate it for the whole domain. We define it like this, and we say as mole fraction. Also show you in the model builder, model assistant, this is where you can find your variables and different variable types. So for example, if I wanted to add mole fractions, you can find the type here. Mass fractions, you can find also mole fractions here, and all different variable types. You can also add descriptions here. You can write your lower and upper boundaries. You can define your spec. Is it either free or fixed? But you can also write it yourself. Let's add now total flow rates on the retentate and the permeate side. As you notice, it's not defined in the component list because this is a total flow rate. Then I'm gonna add other variables. Adding the flux. I defined it as a real variable, but you can also in the model assistant, you can find the flux model type. It doesn't matter that much. This already gives you a very broad range, and it's a quick way to add variables. Then we have temperature on the retentate and the permeate side, and the pressure. Now I'm going to add variables that are needed to calculate permeance. So we have energy of activation, we have a pre-exponential factor. These are the variables that I define here as fixed. So these are the values that we're going to provide to the model. And then we have our permeance and we have our driving force. This is going to be calculated. So I specified it as free. If you do not specify it as either fixed or free, it's going to be considered to be free or calculated. And next are going to be our property procedure variables. So these have to be very specific in terms of the variable types. So for other ones, we can even use a real variable. But if you're calling Aspen property procedures, you need to be specific with your variable types. So if you're going to call molar enthalpies, you need to define a variable type of molar enthalpy. So you can, again, use Model Assistant to find specific variable type. Then let's add result variables. This is going to be total membrane area, hydrogen recovery, and also profit. So this is just a variable that I'm going to use for optimization to show you an example of simple optimization problem. Then I'm going to add parameters. So these are parameters that I'm adding for optimization, but so these are not supposed to present some realistic values, but more convenient for me to show you an optimization problem. And then last and not the least, we need to define our submodel. So how you define your submodel is you define how you're going to call your submodel. So we're going to call it with this, and it's defined from 0 to end node, and we say as permeance. So this is going to be the name of the submodel. So we need to add it here also. So let's add a submodel. So it needs to be called permeance. We're going to add equations later. This is the end of definitions. So let's start with the equation. So first, I like to add the boundary conditions, but in ACM, you're not actually limited with how you add your equation. So you can add your boundary conditions at the bottom or whatever, because this is an equation-based tool. Let's add our boundary conditions on the feed side. So first, we add the boundary conditions at the feed. That's at 0. So our total flow rate at 0 is equal to the feed.f. Why feed.f? Because that's our feed port, and we want to take out flow from the feed port. And you can see how it's designated here in the mole fraction ports SI. So F will be our flow rate, molar flow rate. Then we define our mole fractions. Call it as feed.z. This is how it's defined in the mole fraction port. We add our pressure. So you can see here that we added at 0, but I added pressure and temperature from 0 to end nodes saying that it's equal to phi.p because we're not considering any temperature changes or pressure changes. So we can just say that for the whole domain, our pressure is equal to the feed pressure. And then we need to define our component flow rate at 0. So for all the components at 0, it's equal to the total flow rate times the mole fractions. Then we need to do the same for the permeate side. So unlike for the retentate, we define our boundary conditions at the end node, as you can see here. So we need to define the boundary conditions because this is a counter current system. So in a similar way, we add our flow rates, our mole fractions, our pressure, temperature, and we also calculate component flow rate. Then let's start adding equations in our submodel. But in order to use the submodel, first we need to send the variables to the submodel. So these are going to be variables that we're sending to the submodel. So in the permeance submodel, our energy activation is going to be sent from our main code. In this case, it's not even that convenient to use the submodel. We could just write it in the main code. But for example, if you have a very large model, and for example, if you have a very complex and large kinetic model, you generally want to put that in a submodel in a different code, not to clog up your main code. But basically here, we're going to send these variables, and then we're going to return permeance and driving force back to the main code. I need to close this. So 4. So these variables also need to be defined in the submodel. Let's define it. I'm going to copy the whole submodel at time. So we need to define all these variables. And you can see that, for example, in the permeance submodel, I define T as just T. You can just say that TR is equal to T, so that doesn't really matter. And doesn't which side of equation you write what in ACM. So even that we return this, you can write it in this way. That doesn't really matter. So yeah, we're basically defining again the temperatures, we're defining our total pressure, fractions, energy of activation, pre-exponential factor, and we're gonna use those to calculate the permeance, and also we're gonna use that to calculate the driving force, which is based on the difference in partial pressure. We're gonna compile this. We're gonna close this, and let's compile this also, see if we get any errors. We don't. So for example, if we define this here and we didn't define it in the permeance, we'll get an error that these don't exist. So now let's add our flux. Oh, and one more important thing for your submodel, because your submodel is already defined in your domain from 0 to end node. You don't ever define your domain inside the submodel, because you're basically sending a value and returning a value for each node. So if you define your domain here again, your system would be overspecified. So you do not need to do that because you're defining it already here that your submodel is distributed. So you do not need to define it also in your submodel. So that's an important thing to know. So now let's add our calculation for the flux. So we're going to calculate our flux in the component list and from 0 to end node, and it's going to be equal to the permeance times the driving force. Because our flux on the retentate and the permeate side is going to be the same, so we can just say that flux R for all the components from 0 to end node is equal to the flux P for all the components from 0 to axis P dot end node. And then we can add our balance equations. So this is our species balance. We are adding a first order derivative of flow. And in ACM, this is how you write it. So first order derivative of flow over dx, you just need to write fr dot ddx. So it's a very simple way to write derivatives. But the only variables that can be written this way are the variables that you define this distribution. So you cannot write any other variables like this. You first need to designate them as distribution. So basically, this is going to be df over ddx, and it's equal to minus flux times the membrane area. So we do this from 1 to access our end node. And why we do that? Because we have our boundary condition at 0. So we need to define it from 1 to end node. And for the permeate side, because we have our boundary condition at the end node, we define it from 0 to end node minus 1. So we do the same thing for the component flow rate on the permeate side. And here, the only difference is that we define that it's from J plus 1. So why we do that? Why you don't have to do that, but you can get some inconsistencies. Why? Because we calculate on the retentate side, we calculate our flux and we take our flux from 1 to end node, and on the permeate side, we get it from end node, from 0 to end node minus 1. So we can take the same flux to be consistent. So the amount of, for example, hydrogen that goes to your permeate side or is taken from the retentate side is not different. Of course, the more points you get, the more nodes you use, this is going to be more accurate. Okay, so now we didn't add all the equations, but I'm going to already add the model to the flow sheet to show you that we're underspecified and how to deal with that. So let's add the model to the flow sheet. I always like to add an icon, make it so that it's more visual. Let's fill this, like in the presentation. We can copy this one, make this blue. Then we can add our ports. Our feed is going to be here. Our sweep is going to be here. Our permeate is going to be here. And our retentate is going to be here. Close it and save it. And then we add the model to the flow sheet. This is going to be our membrane model. And you can see here this red triangle. That means that the simulation is underspecified. So we need to add more variables and more equations to this system. And let's do that. But first, let's add our streams. So we can use the connection streams and we can add it to our port. So this is going to be added to the feed port, sweep port, and output ports also. So we can rename this feed. Retentate and permeate. First, what we can do is that we can add our feed conditions and our sweep conditions. So you can see here that these variables are free. So we need to fix them and we need to provide the values. And what you will see also is that the number of underspecified variables is going to drop down from 335. So if we put this to 6, go to 334. So this is the part of the problem that is still underspecified. So let's add that. But I'm going to add it from an Excel sheet because it's faster. These are going to be our feed conditions. We're going to use 30 kilomoles per hour at 20 bar at 100 degrees and 50% hydrogen. So you see now that our number, so that our simulation drop down in terms of the underspecified variables. So let's do the same thing for the sweep. So on our sweep side, we're going to use 15 kilomoles per hour at 1 bar at 100 degrees, pure water. And you will see that our simulation dropped down in terms of underspecified variables. But still, this is not enough. We need to add other equations to the system. So if you notice here, we added the total flow rate only at 0. So we need to calculate the total flow rate for the entire domain. Same for the mole fractions. We already defined our temperature and the pressure for the whole domain. So let's add these two for the permeate and the retentate side. Component flow rates, on the other hand, are calculated through the ODs. So we don't need to define any other equations for that. So let's add total flow rate. So we will calculate it from 1 to end node. It's going to be sum of component flow rates. And we also going to calculate mole fractions based on the component flow rate and the total flow rate. So if we compile again, you will see that the number dropped significantly. So now we're missing only one fixed variable, and I know which one that is, but we're going to add it a bit later. So let's add our other equations that we're going to need. So first, our hydrogen recovery, which is going to be based on the amount of hydrogen that permeated. And let's add our streams. If you notice here, you see that we have an input stream from sweep and feed, but if we double click on the retentate, we don't see anything. That is why, because we didn't define it inside the model. Here we call the ports for the input, but we didn't specify the output port equation. So let's do that first. Going to be our output streams. So we're going to say that the flow rate and end node is equal to retentate.f. So this way, we'll say that our flow rate at the end node is going directly to the output port, and this is where we can get the value. So we do the same for all. And you notice here that I also defined the enthalpies. So we didn't calculate this. So we're going to call Aspen property procedure. How you do that? It's very simple, actually. You use a call function. So in order to calculate the enthalpy at the output, we need a special call, and we provide it with the temperature, we provide it with the pressure, and we provide it with mole fractions. So if you want to check what you need to provide for a specific property, you can go to help, and you can go to contents. You can write property procedure, go to overview, and you can find a specific property that you want to get from Aspen. So for example, we want to get molar enthalpy. So you will see what you need to provide. You need to provide the temperature in Celsius, pressure in bar, and also composition, more composition. This is what you're going to get in these units, and this is how it's going to look like. So you call it. This is the call that you need to give, and this is the conditions that you need to provide. So I do that at input, output on the retentate side, also on the permeate. I also call molecular weights. What you can also do, you don't have to provide it at a single point. So if we define our enthalpy for the entire domain, you define it for the entire domain, but then you also provide your temperature not only at 0 or end node, but you provide your temperature for the entire domain. So that is, again, very useful when you need heat capacities or densities or viscosity. You can just do this, and it's very simple. Then the last equation is going to be the equation that I'm going to use for optimization. So again, this is not supposed to be very realistic. It's just going to be convenient for me to show you an optimization example. So the last variable, so if I compile this, you will see again that we're still missing one variable. This variable is this membrane area. So we're going to use membrane area as both fixed or free variable to show you an example. So let's create a new form where we're going to define our result variables that we're going to use. So you go to membrane, you click on add form. We're going to create a table, and let's call it results. Then you right click, go to properties, variables, and here let's add a few variables. So we're going to add our membrane area. Let's add hydrogen cover. Let's add problem. Now that it's defined, we can go to the model. You right click, forms, results. So we can see it here. So you see that the membrane area is free. So let's fix it. And our model is going to be fully consistent. So now we can actually run the steady state simulation. But first, I still didn't add the values for the energy of activation and other variables. So let's add also that. So let's make a new table for var, and we're going to add missing values for the variables. So properties, variables. So let's add our And let me show you what I mean. Oh. Let's add our energy of activation and Q0. We add energy of activation. So what the star means, it means for all the components or for the whole domain. So the star means everything inside the set. So you said. Click add variable, and then we're going to add Q0 also. So we star, and we can also check the permeance value, which we're going to calculate. But permeance is not only defined in the component list in the main code, but also for the domain. So what we can do is we say Q star star. Then we let's go model forms. Go to this table, and you can see that by default, it added a value of 1. I wrote in the code there they're fixed, which they should be. So because we have a hydrogen selective membrane, we're going to add only the values for hydrogen. So these are zeros, and here I added the values for the hydrogen. And then let's go back to our results. Here, so let's give it a try. Let's say 5 square meter membrane. So let's see what's gonna be our resulting hydrogen recovery. We click play, and the model is solved. So we have about 38% hydrogen recovery. You can also see the permeance values here. Of course, for other components, it's 0 because we only permeate hydrogen. So yeah, what then you can do in terms of variable specifications. So for example, if you want to reach a specific hydrogen recovery, what you can always do is that you can fix recovery, but you can then free your membrane area. So if we wanted 75% recovery, you can just fix that, click play, and it will tell us, okay, for the 75% recovery, you need this much area. What we can also do is, for example, we can fix the area. You can see now that we're overspecified by 1, but then we can free something else. So let's say for 15 square meters and 75% recovery, what would be then the molar flow rate? Then it calculates the molar flow rate at 35 kilmoles per hour. Let's fix this again. So the 30 again. Let's free our recovery again. Yeah, I will now show you also an optimization way how to use optimization in ACM. Because, for example, if you notice here, so let's put it at 8, maybe 5,000, or we put it at, let's say, 20. Again, 5,000, but if we put it at 15, it's going to be higher. So this is not, so we can find what would be the optimal area to reach the highest profit, because of course we want to maximize the profit. So let's go here, we click on the process flow sheet, we go to tools, and we can click optimization. So you can either choose to perform steady state, or you can choose to do a dynamic optimization. Because this is a steady state problem, we do a steady state optimization. We go to the objective function, and our objective function is going to be the profit. So let's add it, because we need to add it from the model. Well, now it's called B1, but we can call it, we can rename it to something else, but let's keep it at B1. So we say B1 dot profit. So it's going to take the profit variable from the model B1 and going to use it as objective function. We say here maximize, because of course we want to maximize it. And then we go to decision variables. So this is where we're going to specify what we're going to vary. In this simple case, we're just going to vary the membrane area. So again, we say B1 from that model, we take AM, and then we add our membrane area here. So you can define your constraints. So what is going to be a lower and upper boundary of this variable? So maybe let's say that we have max 50 square meters. In terms of the control discretization or control variables, we don't need to look at that because this is more for optimization for control. And also with steady state constraints and dynamic constraints, we don't need to define that. So now that we defined our objective function and our decision variables, let's run an optimization. So we go here where it says steady state and we put it to optimization. So play up. Yeah. So now it found optimal point. So our profit is highest when the membrane area is 12.8 square meters. Now that I see that we have a bit more time, and I don't know if there are many questions because I didn't look at the chat.
Oh, there are no questions in the chat.
Oh, okay. Well, maybe then I can show you also how to create a profile plot. So, because we still have 10 more minutes, I was thinking also to do that, but I didn't know if we're going to have enough time. So I hope I was not too fast. So you can also create profile plots in ACM. So maybe we can do that to see in a visual way your driving force, so your difference in partial pressures. So let's create a new variable that's called partial pressure. So we're going to do that on the retentate and the permeate side. So let's create those. We're going to be hydrogen partial pressures on both sides. And let's also add the equation for that. So we can add it, doesn't matter. We can also add it here. In ACM, it doesn't really matter where you add your equations. So we'll say that partial pressure on the retentate side is equal to the total pressure times the molar fraction of hydrogen. We compile again. This off. Let's go to steady state again. Volts. We can leave it at this value. Now, if we want to create a profile plot, go to forms again, membrane, we create a profile plot, call it driving force. Then we can add new variables. So if we go to forms, all variables, we can find partial pressure. Let's take partial pressure on the permeate side of hydrogen. Oh. Here. And then also take PR hydrogen and we carry it here. You need to go to profile variables. So let's call this partial pressure hydrogen. This is PR of hydrogen. And what we can also do is we can add our domain so that we know where it's distributed. So like this, let's add this, call it X. So these profiles are going to go to profiles to plot, and X will go to X-axis. Click apply. And you see we have two different axes. So let's put it in the same one. So in properties, axis map, you go all in one. Now we can also plot our driving force, and we can see our difference in partial pressure. So yeah, that is all that I wanted to show for today. And well, we have a few more minutes, so if there are any more questions, I'll be glad.
Yeah, of course, if there are questions, you feel free to write in the chat. But maybe I was thinking of, since we have a few more minutes, about how to export the model, maybe.
Yeah. So basically, the way you export the model is you go to the membrane. For example, this is our main model. You click right-click, and then you say package model for Aspen Plus or HYSYS. So basically here, you can create a model initialization script, which is going to help it to be solved in Aspen Plus. Basically, it will take the solutions of your OS simulations, or you can choose which solutions you take for the initialization script. You click yes. We say it for B1 because that's the model that we want to use, and we create a script, and then we're going to create this AT_MLS file that needs to be installed in Aspen Plus. But it will also ask us now if we want to install the model right away. So we say yes, and then if we go to Aspen Plus, we can find the model when we turn on ACM models. But yeah. See what was the comment. We will share the team's recording. Yeah, I don't know. We have to agree on that, what to do with that. I don't know. Maybe we can also publish it, and then, yeah, maybe we can put it on YouTube. Let's see. I'll talk to Michaela.
Okay, thank you very much. So let's see if there's any other question. Otherwise, I can make you a couple of very quick questions. Yeah, wonderful presentation indeed, I agree. Just a couple then of quick questions for newly people approaching. So then if it's too long the answer, you can also skip the question. For example, is it possible to add also standard component? Let's say that in my optimization, I need to add a pump to compress the feed. The standard Aspen components are also available in ACM.
You mean like the units here?
No, for example,
like
adding to the flow sheet a pump, a reactor, a heat exchanger.
So it is basically, but it takes 2 licenses. So that is the minus, because what you need to do here is that you need to add, because here now we have a modeler library, and these are the units that we have as an option. So the different control units, for example, PIDs and sums and different types of units that are built in ACM. But you can also add Aspen Dynamics package here. But when you add the Aspen Dynamics package, it takes 2 licenses. So depending on, maybe if you have many licenses, that is not a problem. But generally, I don't like to add it because then other colleagues have problems with using Aspen Plus.
There's a question. Okay, thank you very much from Nestor. So fantastic. I also agree. It is possible to use a feed with properties varying in time. I guess it means a dynamic.
Yeah, so it is. So what you can use is you can use this time data. So in the time data, basically you can define your in configure, you can define your number of points, your sample time. And then here you can, for example, if we say number of points 1,000, here you can define your variable that varies in time. And then you can connect this time data to your model. And then dynamically you can vary it. So you probably have to create few of these time data units. So one to be this flow rate, or this one to be, I don't know, this composition. But yeah, you can do it that way. That's the fastest way.
It's very interesting. Okay, we have 3 more minutes. So if there's any final question, otherwise I still have very few questions. One is, for example, your based on your experience, your suggestion about the number of nodes. Now I think you put 20 in this example.
40.
40?
Yeah. Yeah, I mean, you can also I think maybe the best way is to see what is your model error. So you can calculate, for example, what is the difference between the amount of component that permeates on the permeate and the retentate side, and you can see, okay, if I use 10 nodes, what my result is going to be. It's not always more nodes, it's not always going to be better. So yes, it's going to be more detailed, but it's also more computing power. So you can do quick checks and see where your results are already satisfactory. So maybe you don't need to go above 30 nodes for a certain problem. Maybe you want to go to 100. Or about testing, not that there is like a specific value.
Okay, makes sense. Okay, two more questions. One is it possible the simulation do not converge? Well, that's not only possible, but very common.
Yeah,
And what do you do in this case?
Yeah, that's the biggest part actually of Aspen modeling, because I chose an example here that everything converges right away, of course, but not converging is the biggest part of solving this. But then, yeah, you need to do a lot of tricks. You need to do a lot of initialization. Yeah, that's a question for itself, but not enough time here.
The other one is if you can say a few words about the solver that you're using, solver options.
I think at least for this one, they always have, because basically what ACM does is that when you write your partial differential equations and you choose your discretization method, for example, well, for this one that we chose this, it will discretize the whole domain and it will create a matrix of nonlinear equations. And then, for example, here in the solvers, this is how you're going to solve your system. So generally, what it uses is a mixed Newton method, but sometimes it goes to the fast Newton, depending on the problem. So basically, it will use this method to solve the system of nonlinear equations. And then, for example, if you go to the dynamic mode, then you use an integrator. So generally, I always use this default implicit Euler, and I never had really problems with it. It's fast enough. So this is how basically the dynamics are solved. So for example, in steady state, you solve nonlinear equations, and then you integrate dynamic mode.
Another interesting things to add on this, since we are talking also about solver and convergence, is that there is also when you have to change a variable, say in a broad range, you can use the homotopy setting to change it gradually from one point to another. So please, I don't know if it's relevant, but sometimes when you have a problem of convergence, because maybe you change a variable in too much, let's say, you can gradually change by using the homotopy tool.
Or you can also do it by hand. You can.
Or you can also do it by hand.
Yeah.
Of course. Okay, so it's 12. I don't see the question, although you didn't explain the easiest trick to do that, but we can also leave the people with curiosity.
Oh, I forgot about that. Yeah, yeah, okay. I don't know if, I mean, I can stay for 5 to 10 more minutes. So if everybody wants to stay, I can also show that.
And since it's recorded, it's always useful. In the worst case, even if some people have to leave, I think they can still maybe catch up.
Yeah. So basically, there's something in ACM that doesn't work as it should, but actually works in your favor. Is that when you have countercurrent systems, if you want to be numerically consistent, you would do this. And also, Aspen recommends to do this because you have two domains that have to be solved with two discretization methods, just by the nature of how you set your boundary conditions. But actually, something else works that it shouldn't work, is that you can actually define only single domain. And for example, if we just define this axis R, and then we went to the species balance, and we say set from 1 to axis end node. And we also took this balance on the permeate side. We took this here. We don't need this +1 now. And for example, if I comment this out, I don't know if it will work now because everything else has to be set up in a similar way. But this should never work, actually, because we're solving also this permeate side from 1 to axis end node. And that shouldn't work because we have at end node, we have our boundary condition, meaning that at 0, we're missing a variable. So this should not be consistent. But for some reason, in ACM, it works. I also approached Aspen with this comment, and they said, oh, we don't know, it works. So you basically define one domain, and you, in the species, so in the differential equations, you write it from 1 to end node, even though this one is from 0 to end node -1, still works. Let's compile it. Maybe it will work even now. I'm not sure because yeah, it seems that it will work. Ah, no. Okay. Well, you need to write it from the beginning, and you need to define the single domain. Yeah, basically you can define a single, be it one domain, write your balance equations inside, well, where is it? In the single loop. This will work. What other equations, so like this total flow rate, can be needs to define in this way, so in a correct way. Other equations need to be defined in a correct way, but differential equation need to be defined in the wrong way, and it will work. So yeah, that's a quick tip that you can try. It's also, yeah, much faster and much simpler. And Aspen doesn't know why it's doing that, so yeah.
Oh, that's a very interesting tip. Just a question that came up. You try to solve the system and it says not possible singular decomposition.
Yeah.
This happens when you have some zero denominator for some specific reason.
I mean, here the problem was also that, for example, all these variables are defined in a completely different domain, and I tried to define solve them in XSR, but this is defined in XSP, so that's why. So it can be a lot of different things. But
okay, no, but very interesting. Thank you also for this. You know, if you do your YouTube channel with the video, then you can do a premium contents for the subscriber. And this last 10 minutes with this trick, you will put as a premium comments. No, but thank you very much. I don't see other question, but it was a very interesting presentation. I would have liked to have this kind of presentation before starting my PhD. I would have saved a lot of time understanding ACM. But yeah. If there are no other comments, thank you again. Thank you all the people attending. And well, we look forward to receive your comments, your feedback, suggestions for the next webinars, whatever. And yeah, I wish you all a nice weekend.
thanks, everybody.
Thanks again, Vladimir.
Thank you. Bye.
Thank you. Bye.
Thank you.
Bye
Bye bye.
bye. Bye bye.